Hi everyone, today a video in the Transition Metals and Inorganic Reactions series looking at variable oxidation states. So we talked in the very first video of this series that one of the key properties of our transition metal ions was that they had these variable oxidation states. Quite often there were many different compounds of the same metal that contained that metal in lots of different oxidation states. And we said that while that wasn't so radical in the sense that things like nitrogen, main group elements can have different oxidation states and different compounds, the transition metals show a really wide range of variable oxidation states, and they're actually able to move between these oxidation states very easily. And the key reason for this, again, like we've seen in many of these videos, is it's all due down to really the 3D electrons. And so a typical transition metal will use the 3D electrons and sometimes the 4s electrons in bonding. In the first video of this series, you might have remembered that I said that once we take our isolated metal atom, or our ion, and we then start to put it into the, essentially start to bond it to ligands and put it with other atoms and molecules, that typically we normally thought of our 4s level being slightly below the 3D. Typically, when we actually make our molecules and our compounds, the 3D electrons drop slightly below the 4s. Typically, we often just think about d electrons as being the s and the d in this case. And so, because these 4s and 3d electrons have very similar energies, it's very easy for electrons to be kind of constantly moved throughout the 3d orbitals and also the 4s orbitals. And so they can show a great variety of different oxidation states in different compounds because of the similar energy of those orbitals, because it's so easy to move electrons around. And so you can see this table here of our essentially our D block metals. Remember that scandium and zinc technically aren't defined as transition metal ions because the scandium only forms the 3+ ion, which has a 3D naught configuration. The zinc only forms the +2 stable ion, which makes it a 3D10 system. And so remember that the transition metals had to have this part-filled d orbitals. Now the most common oxidation states for these metals are shown in red. And hopefully what you can notice is there's basically a rise as you go from left to right, from scandium going to manganese. There's this rise, and so you can see that scandium just has +3, titanium +3 and +4 mainly, vanadium +3 and +5 mainly, chromium +3 and +6 mainly, all the way up to manganese, which often shows +2, +4 and +7. But manganese can actually exist anywhere from +2 to +7. Vanadium can exist anywhere from +2 to +5. Just the red ones are the more common that we see. So notice that there is this increase up to +7 for manganese that's in group 7 of the periodic table. And then you can see that as you go from the middle there back down to zinc, that essentially we decrease in the maximum oxidation state we can reach. So iron is then down to +6 as a maximum, cobalt +5, nickel +4, and so you can see that generally it drops back down to having just the kind of +2 oxidation state for the sort of zinc at the end. Now they all show this +2 oxidation state because of course remember that we talked about when we ionize our transition metals to make transition metal ions that it is the 4s electrons that are lost first. And so because they lose these 4s electrons very easily, they all show the +2 state. Also note the existence of the only one there that shows a stable +1 state is the copper. So copper normally exists either as copper 1 or copper 2. And now only the lower oxidation states, normally the sort of +2 and +3 oxidation states, exist as simple ions. So for example, the manganese 2+ ion, the chromium 3+ ion, these have pretty small oxidation states, +2, +3. The higher oxidation states, for example, the Mn7, or the chromium 6, these much higher oxidation states, aren't found as just isolated ions. So you don't find the Mn7+ ion, you don't find the chromium 6+ ion. What you actually find them in is more complex ions, such as the manganate ion, MnO4-, or the dichromate ion, Cr2O7T-. And so if you just kind of review working out oxidation states, you have the MnO4-, your oxygen is normally -2, 4 of them gives you -8. To have a negative charge overall, the manganese must be +7. So that's our manganate ion. And then for the dichromate ion, we have our oxygen again normally being -2, 7 of them, so -14. To have a -2 charge overall, each chromium has to be +6 to give +12 overall. Now, one of the most interesting examples to look for variable oxidation states is actually to look at vanadium. So we saw for the vanadium that we could take essentially any oxidation state from +2 all the way to +5. Now, the species in the oxidation states of +4 to +2 are formed from the reduction of the +5 oxidation state, what we call the vanadate ions, by normally zinc in an acidic solution. So we can reduce our vanadium +5 oxidation state to either the 4, 3 or 2 using zinc in acidic solution. And the usual source of vanadium 5 is in a compound called ammonium vanadate. That's NH3,4VO3. So if we think about our sort of charges on this, we have our ammonium ion, which is a positive ion, NH4+. That means for that to be overall neutral, our VO3 ion must be overall negative. Oxygen normally -2, so we have 3 of them to give -6. And therefore, to give a -1 charge overall, the vanadium would be +5. So that's our ammonium vanadate and our vanadate ion. And then you can see in this table here, I've given you the oxidation state of vanadium from 5 down to 2. Now, you can see here that the vanadium in the +5 oxidation state can also exist as VO2 H2O4+. Now, the exact vanadium ion that's present can vary with the pH of the solution. It can vary with what the reducing agent that we use is. But typically, the main ion is this called the dioxovanadium ion. Again, it's vanadium in the +5 oxidation state. And so we can find this vanadium either in the ammonium vanadate or as part of this, essentially what was a hexaaqua ion that's been oxidized, essentially. So this VO2 plus ion, and then the H2O4, essentially we can think of this as being some sort of aqua ion. Now, the actual colour of that vanadium in the +5 oxidation state here is a yellow colour. So what we can imagine is we take our ammonium vanadate, we dissolve it in our acidic solution. This will be typically an aqueous solution, so it has water involved in it. And like we said back in the first video of this series, if we take a transition metal salt, dissolve it up in water, typically what we actually form is our aqua ions. We've talked previously about making things like the chromium, iron, hexaaqua ions, 6 water molecules. Here we have our vanadium, we have VO2, so 2 of the sites of this octahedral complex are taken up by oxygens, and so therefore we can only fit 4 water molecules around, so you essentially have a tetra aqua ion. And so this vanadium 5 VO2 H2O4+ is our yellow colour. Now, we can, as I said, reduce this with our zinc in acidic solution, and we can actually reduce it down to the +4 oxidation state. This exists as VO H2O5 2+. So you can see all we've done here essentially is you can imagine we've lost one of those oxygens from the VO2, and we've added a water molecule. So we've lost one of those oxygens. We can think of it being reduced because we've lost oxygen. And so this ends up now being a blue ion. So the colour of the solution is blue. And it's important here not to get confused with the actual ions that exist. So if you take away the waters and just consider them as the kind of simple ions, in the +5 oxidation state, you have the VO2 singly positive ion. The vanadium in the +4 oxidation state, this blue solution, you have the VO 2+ ion. To make sure you know whether it's a 2+ charge or a VO2 +1 charge, essentially. We can then keep on going and get all the way down to the vanadium 3 oxidation state. Here we just have the very simple vanadium 3+ ion, V3+. And again, we can think about our reduction here as a loss of our oxygen. And so we've lost that oxygen from the VO ion to become just V. And now we have our vanadium hexaaqua ion. That's green. And then we can go all the way down to the lowest oxidation state, the vanadium 2. And this again is a hexaaqua ion, but now it's a 2+ ion, not a 3+ ion. And the 3+ is green, the 2+ is purple. Now, when we do these reactions, we normally stopper them with some cotton wool. Now, this allows the hydrogen that's produced, and the hydrogen gets produced from the reaction between the zinc and the acid. That normally ends up producing some sort of zinc salt, some sort of hydrated zinc salt and hydrogen gas. The cotton wool allows this hydrogen gas to escape. If we just stoppered it with a normal sort of full-on stopper, you'd have a build-up of pressure, and that would be dangerous. So we use the cotton wool that allows this hydrogen gas to escape, but it doesn't allow too much oxygen in. And the key thing for this is that if we allow our oxygen in, this would reoxidize the lower vanadium oxidation state. So let's say we've got all the way down to our V2 plus oxidation state, our 2 plus vanadium oxidation state. Without that stopper in there, the hydrogen can escape, but also the oxygen can get in and oxidize it potentially all the way back up to that vanadium plus 5. And so if you take the V2 plus ion and leave it open to air, it very quickly goes from looking purple to the green V3 plus ion. Now the reason that we use zinc actually goes back to thinking about electrode potentials and electrochemistry. So if you're not feeling so confident on your electrochemistry, you can go back to my series of videos on electrochemistry and electrochemical reactions. But the key thing is that our zinc has a very negative electrode potential. What we mean by that is it's a very good reducing agent. It's very good at losing electrons itself and therefore reducing something else. So this is what we want to do. We want to reduce our vanadium. So we can think of this in terms of losing our electrons, but also from a more technical point of view with our redox. We know that from oil rig, oxidation is loss, reduction is gain. And so we want to reduce our vanadium by making it gain electrons. And therefore we need something that's a very good reducing agent, something that's very happy to lose electrons. And this turns out that zinc is good for this because it has a very negative electrode potential. And so you can see at the bottom there the zinc electrode potential. Remember that these electrode potentials are always written as reductions. So we have our zinc 2 plus 2 electrons to make the zinc metal. This has this half cell potential of negative 0.76 volts. The actual vanadium equation we have at the top, so this is our VO2 plus. This is our vanadium in the plus 5 oxidation state. Plus 2 hydrogens plus our electron produces the VO2 plus ion. That's going from the plus 5 to the plus 4 oxidation state, the yellow to the blue solution. And that this has a half cell value here of 1 volt plus 1 volt. And so the way to remember it is always that the negative one loses electrons. It is the one that is essentially oxidized. The one that has the more positive value is the one that gains electrons. It's the one that is reduced. So the more positive value gains the electrons, the more negative one loses the electrons. It's a better reducing agent. Very simple way that I remember it is that the more negative one is probably going to lose electrons because negative repels electrons, positive attracts electrons. And so if we then essentially, if we want our zinc equation here, we need to flip it around the other way because we're having the zinc lose electrons because it's a reducing agent. So we flip that the equation around, we multiply that top vanadium equation by 2. That will allow us to cancel out our electrons. And when we do that, we end up with an overall equation that is zinc plus 2 of the vanadium ions in the plus 5 oxidation state, the VO2 single positive charge, plus 4H plus going to zinc 2 plus, 2 lots of the vanadium in the plus 4 oxidation state, the VO2 plus ion, and then 2 lots of water. And remember that when we calculate our E cell values, we do the cell of the right minus the cell of the left. In this case, that means that when we put our numbers in, it actually comes out to be positive 1.76. So quite a high E cell value here, showing this is a very feasible reaction. Now, the reason we use zinc is because if we have reducing agents that have slightly less negative electrode potential values, they can't complete all of the reductions. And so what I've shown you here is essentially the electrochemistry for that first reduction, from the plus 5 to the plus 4. But we can think about going all the way down to the plus 2 ion. And the key thing is that we always need our vanadium potential to be the more positive one. We always want our vanadium to be the one that is being reduced, gaining the electrons. For that to happen, the other metal we're using to reduce this, the zinc in this case, has to be more negative in terms of its electrode potential. So there are other metals, for example, you can get some of the earlier ones reduced using tin, for example, in acid solution. But the later ones, tin just simply doesn't have a negative enough electrode potential. There comes a point where the tin has the more positive, and the vanadium has the more negative, which is the wrong way round. We always want our vanadium potential to be more positive than the other. Now, we can think then about doing redox reactions with transition metals, and many of the reactions are actually redox reactions. And so it's useful to use half equations for these to see essentially whether we're oxidizing or reducing, and then being able to construct a full balanced equation. So for example, we have potassium manganate, that's our manganate 7 ions, MnO4-, and these can act as an oxidizing agent in acidic solution. So for example, it might oxidize Fe2+ to to Fe3+. Now again, note here that our reaction for the manganese is that we have our manganate ion, the manganate 7, MnO4-, going all the way down to Mn2+. Now note again here that your lower oxidation state of the Mn2+ exists as the simple ion. The MnO4- actually exists as our complex ion, essentially. So the high oxidation state is bonded to other atoms. So we balance our half equations by a general procedure. And this goes back again, if you're not so happy with half equations and redox chemistry, go back to my series of videos on redox chemistry. But the first thing we want to do is make sure that our metal atoms are balanced. In the case of the MnO4- going to Mn2+, we have one manganese on both sides, so that's balanced. The second thing we have to do is we have to add water to balance the oxygens. Now, if there's no oxygens present, you skip this step. However, we have MnO4-, so we have 4 oxygens on the left-hand side, none on the right. So we have to add 4 water molecules to balance those oxygens. So 4 H2O would go on the right-hand side. Then, if you have any hydrogens present, which we do now because we've added water, we have to add H+ ions. This is normally why we do these in acidic solution. In the previous example, we had this reduction of the vanadium in acidic zinc solution. And so we add H+ ions to balance out the hydrogens. And so in our case here, we added 4 hydrogens to the right-hand side to balance the oxygens. Added 4 water molecules, to balance out the oxygens. Therefore, we have 8 hydrogen atoms essentially on the right-hand side. So we have to add 8 H+ ions on the left-hand side. And then the final thing to do is to simply add electrons to balance the charge. So like this is any kind of normal equation, we have to make sure that our atoms are our charge balance on both sides. And so in this case, we'd have a 2+ charge on the right-hand side. To get the left-hand side to have the same 2+ charge, we'd have to add 5 electrons. And so our balanced half equation here is MnO4- plus 5 electrons plus 8H+ going to Mn2+ plus 4H2O. So always follow that general procedure. Balance the metal atoms. If there's any oxygens present, balance it with water. If there's any hydrogens present, balance it with H+ ions, and then make sure the charge balances by adding electrons to whatever side needs it. Now the half equation for the other species here, the iron, is much simpler. We have Fe2 going to Fe3+. That oxidizes this iron. We've lost electron. And so our equation just becomes essentially we don't have to worry about balancing our metal atoms. We don't have to worry about adding waters because there's no oxygen. We don't have to worry about adding protons because there's no hydrogens. So all we have to do is just balance the charge by adding an electron to the right-hand side. And then to construct our full balanced equation, we have to ensure that our electrons in each equation balance. So we have the same numbers of electrons in each equation, and then we combine the equations. So you can see here that for the manganese equation, we have 5 electrons. For the iron equation, we have 1 electron. So we need to multiply our iron equation by 5 to get 5 electrons. Once we multiply that by 5, we can simply add the two equations together. So you write everything that's a reactant on the reactant side, everything that's a product on the product side, and by combining it, you end up with 5 Fe2+ plus MnO4-, our manganate ion, plus 8H+, going to 5 lots of Fe3+, plus Mn2+, plus 4 H2O. So we've oxidized our iron, Fe2+ to Fe3+, and we've reduced our manganese, essentially going from the manganate 7 down to the manganese 2+ ion. Now, there are lots of different ones to know for these, lots of different examples they could give you of various atoms being oxidized and reduced. The other really useful one to know is actually our reduction of the dichromate anion, Cr2O7 2-, sort of orange-coloured ion, being reduced to the chromium 3+ ion. Again, this means it can act as an oxidizing agent, oxidizing something else and being reduced itself. And hopefully you recognise this change as being when we oxidize alcohols up to either primary alcohols up to aldehydes or carboxylic acids, or secondary alcohols up to ketones. This is the oxidizing agent we use normally, acidified potassium dichromate, so K2, Cr2O7 2-, acidified with sulfuric acid, dilute sulfuric acid. And we talked about in those reactions that the key observation that we saw if we've oxidized our alcohol was that we have this colour change from orange to green. And that's because we've had our alcohol oxidized up to some sort of carbonyl compound, and we've had this chromium reduced from chromium 6 down to chromium 3. Now the next thing to talk about is doing redox titrations. So doing redox titrations with transition metals, it's very similar to doing an acid-base titration. So if we think back to an acid-base titration, we normally have maybe an acid of an unknown concentration. We take a base of a known concentration, react a specific volume of that base with a specific volume of the acid. We normally have an indicator present as well, where we see this a colour change that tells us that we've reached what we call our equivalence point or our neutralization point. And then from using our mathematical skills that we know that the moles equals the concentration times the volume, and we use the mole ratios that are present in our balanced chemical equation, we can work out what the concentration of this acid was. Now in a redox titration, we're not using an acid and a base, but an oxidizing agent and a reducing agent. So something that gets oxidized, something that gets reduced. And this is useful to be able to calculate the amount of a particular agent in solution. So an example is that we can use the equation we've just previously worked out, that half equation for the manganate ions being reduced to the Mn2 plus manganese ions. And we can think about if we had a burette, we can use that burette to add a solution of our potassium manganate to a solution that contains, for example, chloride anions. Now we know the concentration of our chloride anions, but we don't know the concentration of our potassium manganate solution. We've also acidified this with excess dilute sulfuric acid, and actually there's no indicator required here, and typically for a lot of redox titrations we don't require indicators because we have a natural colour change already present. One of the key things here with using transition metals is of course that we have variable oxidation states, but also ions that typically are coloured, and typically different oxidation states have different colours. And so in the case of this one, we have our deep purple colour of our manganate anions, that Mn in the 7 plus oxidation state, turning to the almost colourless, very pale pink colour of the manganese 2 plus ions. So we have a natural colour change anyway, so we don't need to put an indicator in. And so in terms of the acid here, we have to use sulfuric acid rather than hydrochloric acid. The reason for this is because the hydrochloric acid will be oxidized by the manganate ions, and this will give false results by introducing essentially introducing chlorine into our system. Now this can be calculated by looking at the EMF values of the half equations for the hydrochloric acid and for these manganate ions here. I'm not going to go through this here, but you'd be able to see that essentially it would oxidize up the hydrochloric acid, which is not what we want, give a false positive. So we have to use sulfuric acid instead, which isn't going to be oxidized by our manganate ions. And so we have our two half equations here. We have our manganate half equation that we've worked out on the previous slide. This has a potential here of plus 1.51 volts. We then have this chlorine half equation. Again, these are both written as electrochemical reductions. We have a half cell value for this being 1.36 volts, positive 1.36 volts. And so remember that the more negative one is going to be the one that releases the electrons. It's going to be the one that is oxidized, the better reducing agent, while the more positive one is the one that is going to be reduced. And so in this case, this works very well. We have our manganate equation being the more positive one, being reduced. That's what we want. We want to reduce our MnO4 minus down to Mn2 plus. And therefore, we're going to actually oxidize our chlorine equation. So we're going to have to flip our equation around. So we're going to have chloride anions releasing electrons and producing Cl2. So we're going to flip that equation round. Our manganate one we keep written as a reduction. And then remember to create the overall equation, we need to make sure that our electrons balance so they can cancel out. So we have to multiply this chlorine equation by 5 to get 5 electrons that will cancel with the 5 electrons in the top equation. We then add together all of the reactants on the reactant side, add together all the products on the product side, cancel out the 5 electrons on both sides, and our overall equation comes out to be 5Cl minus plus our manganate ion plus 8H plus going to 2.5 chlorines plus Mn2 plus 4H2O. And again, we can work out our standard cell potential here. And in this case, it ends up coming out to be plus 0.15 volts. Now, I've not drawn out, obviously, the actual sort of When we calculated E cell values in the electrochemical videos, we looked at drawing them out in a specific orientation, that the thing that was reduced goes on the right, the thing that was oxidized goes on the left. Remember that when we work out our E cell values, we do the right minus the left, and the right is what's reduced. So our manganate equation minus the chlorine equation gives you an E cell value of plus 0.15 volts, a feasible reaction. Now, some transition metals are able to undergo disproportionation reactions. Now, if you remember, disproportionation reactions are reactions in which one species becomes both oxidized and reduced. So it's not like in these examples that we've had above here, where, for example, the manganate ion gets reduced and chloride gets oxidized. That's two separate species, one of them being oxidized, one being reduced. We actually have a particular element both being oxidized and reduced in the same reaction. And so our example here is this copper oxide, copper in the Cu2O. Oxygen is normally -2, and so that means that our copper here must be in the +1 oxidation state. We react that with sulfuric acid, and we actually end up producing copper sulfate, and H2O. Now, copper metal is kind of sort of brown. Copper sulfate, of course, probably know as a blue solution. And then we have water as well. And if you work out the oxidation states of the coppers, we've gone from +1 on the reactant side. Copper metal, just being on its own, has an oxidation state of 0. So we've gone from +1 to 0, and so therefore we've gained an electron, must have been reduced. And then we have our copper in the +1 oxidation state going to copper in the +2 oxidation state in copper sulfate. So +1 to +2, it must have lost electrons, and therefore it's been oxidized. But the key thing is that the copper has been both oxidized and reduced, so it's a disproportionation reaction. So now we can actually start to think about doing our redox titrations, actually doing some maths on these the actual questions. So the actual maths of these questions is typically nothing new than what you've seen throughout your A-level. If you go back to doing acid-base titrations that you probably did in the first year of A-level, the maths isn't really any different. We need to work out the moles using the concentrations and the volumes that we are given. And the key thing is that we need to use the mole ratios in the question to be able to then work out the other quantities. Now, a really common mistake with these types of questions is to always triple check what volume you are dealing with. Often questions will be worded in the way that they will sort of take you through how these redox titrations work, and they will ask you for the concentration of a starting 250 centimetre cube stock solution, for example. But typically the titration is carried out using a 25 centimetre cubed portion of that stock solution. So you created up your stock solution, you've then taken a small quantity, 25 centimetres cubed, out of that to do the titration with. And so the key thing to remember is always remembering, well, what is the volume that I'm actually dealing with? Typically, when you work out the moles in the titrations, you're dealing with the smaller quantity that you've used in the titration. But if the question asks you for the concentration of the starting stock solution, you have to remember to multiply the moles by 10 once you've worked them out, because the starting solution had 10 times the amount of the amount that you used in the titration. So an example might be an iron tablet, which is mainly iron sulfate, FeSO4, was dissolved in excess sulfuric acid, and the solution made up to 250 centimetres cubed with water. So that's creating our stock solution. We've then taken 25 centimetres of that solution. We've taken 25 centimetres cubed of that stock solution, and that was what was titrated with a 0.001 mole per decimetre cubed potassium manganate solution. And we're told that exactly 25 centimetres cubed was required for a colour change. What was the mass of the iron in the tablet? So the way that we need to go about this is using the skills that we've just been using all the video. So we take our half equations. Now typically I think this manganate equation is one that you need to remember. So it's MnO4- always going down to Mn2+. The iron equation is what we saw earlier on. They'll probably give you that in the question. So Fe2+ going to Fe3+. So we do what we've done in the previous few slides. We balance our half equations. I'm not going to go back through it again. Balance it up with waters and hydrogen ions and electrons to make sure that all the atoms and charges balance. We end up with these two half equations. To combine them into the full equation, remember we have to get our electrons to balance, so we need to multiply this iron equation by 5. Write all the reactants on the reactant side, all the products on the product side. Cancel out your electrons on both sides, and your actual overall equation here comes to be our manganate ion plus 8H plus going to 5 Fe2 plus, plus 5 Fe2 plus going to our our manganese ion Mn2 plus, 4 H2O and 5 lots of Fe3 plus. And so really the two equations that we really need to use here are our mole equations. Remember, there's two forms of the mole equation. There's the mole equation for solutions, which is concentration times volume. Remember that if we're dealing with that, we have to always think about our units. Concentrations are in moles per decimeter cubed. Volumes are typically given in centimeters cubed. So we have to convert our centimeters cubed volume into decimeters cubed by dividing by 1,000. And the other mole equation is moles is the mass divided by the molecular mass. So, even in questions like this, and as I always recommend with mathematical questions, even if you're not sure how to start a question, simply use the data that you've been given in the question. So you're told a volume and a concentration for the potassium manganate. If you have a volume and a concentration, you can work out the moles. Even if we're not sure what we're going to do with it, work out the moles. You'll get a mark for doing that. And so our moles of potassium manganate, we're given a concentration and a volume, so we use the N equals C times V, remembering to divide by 1,000 to convert our centimeters cubed volume into a decimeters cubed volume. So we do 0.001 times the 25 divided by 1,000, and this gives us 2.5 times 10 to the minus 5 moles. So that's our moles of potassium manganate. What we want, though, is to be working out the mass for the iron. We want the iron tablet mass, essentially, the mass of the iron in the tablet. So we have to then think, this is where it's really important to use our mole ratios. What's the mole ratio of the manganate compared to the iron 2 plus? And you can see from our overall balanced equation that we have 1 mole of manganate, MnO4 minus, reacting with 5 moles of Fe2 plus. So to work out the moles of Fe2 plus, we simply multiply the moles from the previous line of working by 5. That gives us 1.25 times 10 to the minus 4 moles. Now this is the point where it's really important to remember what volume you're dealing with. And typically sometimes, I haven't drawn it on here, but sometimes in questions like this I'll actually draw a little diagram out to remind me the steps. We've made our 250 centimeter cube stock solution from our iron tablet, and then we've taken a small portion of that 25 centimeters cubed, a tenth of it, out to do the titration with. So this moles of Fe2 plus that we've worked out is actually for the 25 centimeter cubed solution, because it's what our moles have been worked out from the titration data. However, the question asked us for what was the mass of the iron in the tablet. That tablet was dissolved in the 250 centimeters cubed. So we need to multiply the difference, the 25 centimeters cubed going into 250 is 10. So there's 10 lots of that in our 250 centimeters cubed solution. So we multiply our answer by 10. And so the moles of the Fe2 plus in the original 250 would have been 1.25 times 10 to the minus 3 moles. And then once we have the moles of our iron 2 plus, we can then work out the mass of the iron. And so therefore we just need to use our moles is mass divided by mR, rearrange it for mass, so mass is moles times mR. And so we do the moles multiplied by the molecular mass of our, we're concerned about the iron, the Fe, which is 55.8. And therefore we take the 55.8 multiplied by our moles in 250 centimeters cubed, and that gives us 0.0698 grams. And again, watch the significant figures. We can only give our answer to the minimum number of significant figures in the question. The 250 centimeters cubed is a 3 significant figures. Our 25 centimeters cubed is 4 significant figures technically, and our 0.001, notice we have 2 zeros at the end of that, that's also a 3 significant figure number. And so therefore the minimum is 3, so we give it to 3 significant figures, 0.0698. And so the final thing to talk about here is actually how we oxidize our transition metal ions in alkaline solution rather than acidic solution. So we saw just now that the high oxidation state of our manganate ion, our MnO4 minus, our manganese here in the 7 plus oxidation state, was reduced in acidic solution. We also saw that that could happen if we had our dichromate anion. Our chromium in the +6 oxidation state, again a very high oxidation state, was reduced in acidic solution. The oxidation of lower oxidation states, transition metal ions, normally happens though in alkaline solution. And this is because there's a tendency to form negative ions in alkaline solution. And since oxidation is the loss of electrons, remember oil rig, oxidation is loss, the loss of electrons is easier from a negatively charged species than from a neutral or a positive one. You can think of this as being, if it's already negatively charged, it's happy to lose electrons because we have this kind of repulsion between the electrons that are negatively charged and the actual negative charge overall on the ion. It's happy to lose the electrons, essentially. And so if we take us just a kind of an overall 2+ ion, if we're in an acidic solution, that normally exists as our hexaaqua ion, the H2O6 2+ ion. In a neutral solution, this would be typically our precipitate of this, so our neutral metal hydroxide precipitate. So we can normally think of that as sort of being MOH2. But of course, remember that we're in aqueous solutions, so we also have our water molecules there as well. So MH2O4 OH2. In an alkaline solution, we typically end up forming negative ions. In an acidic solution, we normally form positive ions. Alkaline solution, though, is normally negative ions. And so therefore we end up forming this MH2O2 OH4 2-. So now we've essentially gained more of those OH-, those alkaline OH-. And so the low oxidation states of transition metals, for example the Fe2+, they're often stabilised against the oxidation by air. So if I left Fe2+ ions just in open to air, these would be quite quickly oxidised up to the Fe3+ ions. Now they're often prevented against this oxidation by air by keeping them in an acidic solution where it's harder for these things to be oxidised. Typically, we reduce things in acidic solution, we oxidise things in alkaline solution. And so to oxidise a transition metal state up to the high oxidation state, so let's say we're going from our chromium 3+ up to the chromium 6+ in our dichromate, or the manganate 2+ up to the Mn7+ in our manganate ion. Often an alkali is added, followed by the oxidising agent. And the alkali essentially forms our negative ion. We then have our oxidising agent where it's easier to actually oxidise that metal because it's from a negative ion. And so an example is the oxidation of this cobalt 2+ ion to the cobalt 3+ in alkaline solution. And so you can see here we have our cobalt with 6 hydroxide ligands, OH ligands, that's a 4- ion. We have our hydrogen peroxide, and then this ends up oxidising, hydrogen peroxide ends up oxidising this alkaline solution of our cobalt up to the cobalt 3+ ion. So again, you can see there that we have this same the same ligands, essentially 6 hydroxides. We've just gone from a cobalt 2+ ion to a cobalt 3+ ion. Now, if we're in an ammonia solution, these cobalt 2 ions can actually be oxidised by oxygen in the air. And if we use an excess of ammonia solution, then we have a ligand substitution reaction taking place where we end up then producing our cobalt hexaamine complex, cobalt NH3 6 2+. These are brown. And if we have these hexaamine complexes, they can be oxidised by the oxygen in air. They're not protected by being in this alkaline environment. They're not protected in that way, and so they can be oxidised by air up to the cobalt 3+ ion. So we now have our cobalt NH3 6 3+ ion, and this is a yellow colour. So time to have a go at a question. Just one question this time, but it's going to use all the skills that we've talked about in this set of videos. So it's a redox titration question calculating the percentage of iron in a steel wire. So the unbalanced half equations are given there. So have a go, pause the video, and the answers will be on the next slide. So this is very similar to the example we did earlier on. Now we're using actually our chromate half equation rather than the manganate half equation. But essentially all the steps that we did before apply here. So we're going to think about having our half equations, balancing these half equations by adding our waters, our hydrogen ions, our electrons in to make sure the atoms and charges balance. We're then going to combine our half equations, making sure the electrons balance to get a full equation. Then we're going to use the data in the question to be able to work out moles, use the mole ratios, and eventually get to our answer here that it wants the percentage of the iron in the steel wire. So we have our two half equations. So the first one is the iron being oxidised from Fe2 to Fe3+. That's a very simple one to balance. We don't have to worry about waters or hydrogen ions because there's no oxygens or hydrogens. We just add in our one electron to balance the charge. The dichromate one is a bit more difficult, so we have Cr2072-, the dichromate, chromium 6+, being reduced to chromium 3+. Now the first thing to remember from that list was to always make sure that our metal atoms balance. So the first thing to notice here is that we have 2 chromiums on the left and only 1 on the right. And so we have to put 2 Cr3 on the right hand side. We then have 7 oxygens on the left hand side, so we balance our oxygens, remember, with water, so 7 H2Os on the right hand side. We've then introduced 14 hydrogens on the right hand side, so we have to add in 14 H pluses on the left hand side. And then finally we have to balance up our charge, so on the right hand side we have an overall 6+ charge. To get an overall 6+ charge on the left hand side we have to add in 6 electrons. Then we note the 6 electrons in the bottom equation, only 1 in the top, so we need to multiply our ion equation by 6 to get 6 electrons. Once we then combine these half equations, so add all of the reactants together on the reactant side, add all the products together on the product side, we end up with our full equation. We cancel out our 6 electrons on both sides, and our full equation is 6 Fe2+, plus our dichromate anion, plus 14H+, going to 6 Fe3+, 2 chromium 3+ ions, and 7 waters. And so the key thing here is that we can see we have a 6:1 ratio of our ion to our dichromate. So in the question, we were told that we had our steel wire, which steel is mostly iron mixed with a bit of carbon. We have a mass of 3.225 grams, dissolved in dilute sulfuric acid and made up to our 250 centimetre cube stock solution. So here we go. I'm going to draw a picture of this to help me remember what kind of volume I'm working in. So I take my steel wire, I dissolve that up in 250 centimetres cubed to make my stock solution. I then take a 25 centimetre cubed portion of this and use it in my titration. So I'm going to draw essentially an arrow showing that I'm taking 25 centimetres cubed out of that, and then I've drawn my sort of little very rubbish drawing there of a burette to indicate that I'm doing the titration with that 25 centimetres cubed. And we were told that it required 31 centimetres cubed of a 0.031 mole per decimetre cubed concentration solution of our potassium dichromate. So again, even if we're not sure what to do, use the data the question gives us. We've given a concentration and a volume for the potassium dichromate, so we can work out the moles. That's by doing our moles is concentration times volume, remembering that we have to turn our volume from centimetres cubed into decimetres cubed by dividing by 1,000. So we put those numbers in, the 0.031 multiplied by 31 divided by 1,000, and this comes out to be 9.61 times 10 to the minus 4. We then use our mole ratios here, so for every 1 mole of our dichromate, we have 6 moles of iron 2+. And of course, that's actually what we want. We want the percentage of iron in the tablet, so we want to work out the mass of the iron, so we need our moles of the Fe2+. So we now essentially just use the mole ratios here. 1 mole of dichromate is 6 moles of iron, so therefore 6 times that mole value gives you 5.77 times 10 to the minus 3 moles. We then have to consider the volume that this is in. This is all to do with the titration that we've done, which was in 25 centimetres cubed. We want the mass of the iron that was dissolved up in our 250 centimetres cubed. So again, we have a sort of 1 in 10 ratio here. We've taken out a tenth of this for using the titration. So our stock solution is 10 times the amount we've used for our titration. And so the moles in the stock solution will be 10 times the amount that we had for our titration as well. So the moles of iron 2+ in our 250 centimetre cube stock solution is 5.77 times 10 to the minus 2 moles. Then finally, if we want to work out the percentage mass of iron in the steel, we need a mass to be able to do that. We were told the mass of the original steel wire. We want the mass of the iron in that steel wire, essentially the percentage of it. So we need to work out the mass of the iron by doing moles times the MR, rearranging that N equals M over MR equation. Putting those numbers in and using the MR here for just the iron, so Fe2+, gives us 3.217 grams. And again, always note the significant figures. If you go back to the question, all the data we were given was to 4 significant figures. So I've given my answer here to 4 significant figures, 3.217 grams. That's not the end of this question though. We won't ask for the mass of the iron, but the percentage of the iron in the steel wire. And so to find the percentage of it, we're going to take the actual mass of the true iron, divide that then by the steel mass, and you can see that by times it by 100, you get 99.8, which is about right. We know that steel is mostly iron with a little bit of carbon. So our percentage of iron in our steel wire is 99.8%. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on the tuition website. I offer online tuition for chemistry, so you can check out those pages for prices and how to contact me. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.